Hi, my name is Lorena. I'm doing a PhD at Imperial College London regarding phase equilibrium measurements and modeling of CO2 and lighter gases. Phase behavior is of crucial importance in the development of a number of processes, particularly in the design, optimization, and safety of high-pressure chemical and separation. Processes like enhanced oil recovery, biomass gasification, carbon capture and storage, and the transportation and storage of natural gas demands accurate phase equilibrium data in order to predict the behavior of the real systems. So even though computational methods for the prediction of phase behavior have made considerable progress in the past decades, the experimental determination of phase equilibrium remains an indispensable source of data. This is because deviation from ideality are stronger at high pressures than ambient or lower conditions, and the phase equilibrium is often more complex and difficult to predict with thermodynamic models only. Combining experimental phase equilibrium data with thermodynamic models, such as equation of state, can reduce the amount of experimental data needed to describe the system. In addition, adjustment of interactive parameters in thermodynamic models requires some experimental data points. So my PhD project focused on vapor-liquid equilibrium experimental measurements of relevant mixtures to carbon capture and pipeline transportation of gases. These gases include CO2, methane, hydrogen, nitrogen, argon, CO, and oxygen. All measurements were carried out with the state-of-art high-pressure and low-temperature vapor equilibrium apparatus. For safety, the whole apparatus is inside a film cupboard. My PhD project comprises the measurement of 7 isotherms of 2 different binaries, methane CO2 and CO CO2. Furthermore, hydrogen and CO2 and nitrogen and CO2 was previously measured in our group. So we start the vapor-liquid measurements by introducing CO2 into the cell. By using an intermediate half-liter reservoir, we can calculate approximately the quantity of CO2 injected into the cell. We need the cell to be half full with liquid CO2 before introducing the secondary gas. Then the lines are pressurized with the secondary gas from the gas cylinder, and the secondary gas is introduced into the cell until the desired pressure. So we wait for equilibrium, set the open time of both liquid and vapor sampling valves. The sample will be then sent to a previously calibrated GC for quantification. So here you can see the detect response area of both components. For discharging flammable mixtures, it needs to be burned before venting into atmosphere. If you're interested in more information, please go to our website.